In this video, I'm going to show you how, with zero CNC experience, I managed to make a professional bike chainring using only free software and machining it right here in my bedroom. I'll start by introducing my CNC machine, then walk you through the entire process. From choosing the material, explaining the design, 3D modeling, creating the G-code, and finally machining the part. Let's get started. For this first CNC experience, I'm going to use the Carvera Air from Makera, which was kindly sent to me for free. Just a quick disclaimer, I'm not being paid to talk about this product, and Makera gives me full freedom to share my honest opinion. They will be watching this video at the same time as you. The CNC comes in a fairly compact box, but oh boy, it's heavy. I don't recommend skipping arm day, otherwise you'll have a hard time getting it into your house. Once unboxed, the CNC is completely plug and play. You don't need to assemble anything yourself, everything is ready to go. If you get lost, you can also follow the setup guide, which is really well detailed and nicely illustrated. Personally, I had no trouble setting it up at all. In fact, there are only two things you'll need to assemble yourself. The emergency stop button, which is just a cable to plug in, and optionally the arm where you can mount a tablet or smartphone to control the machine. The machine also comes with all the tools you need to secure your stock, so it doesn't move and ruin the machining or one of your bits. And believe me, I've learned this the hard way, as you can see from this mishap. The Carvera Air comes with a set of 10 of the most commonly used 1/8-inch bits. You can find other models on their website or use your own. It also supports different bit diameters: 1/4-inch, 4mm, 6mm, and 1/8-inch by using separate spindle collets. As for the dimensions, the CNC has a footprint of approximately 50 by 50 by 45 centimeters. In my case, I placed it on an IKEA lac coffee table and it fits perfectly. It has a maximum working area of 30 by 20 by 13 centimeters. And as you'll see in my project, I made full use of that space. You could say it's a small but very sturdy desktop CNC. It's equipped with a 200-watt motor that can reach up to 13,000 RPM in closed loop. This means it can machine almost any type of material, from wood and copper to aluminum and steel, using light passes and low speeds. For me, the two main strengths of this machine are the quick release tool, which lets you change bits effortlessly without any tools, and its robust die-cast frame that ensures sturdiness and reliability. There is absolutely no play anywhere, which allows for great precision during machining. You'll see this later on. Alright, now that we've covered the machine itself, let's move on to the project. Since CNC is something completely new to me, I wanted a moderately complex project that I could actually test afterwards. So I decided to make a bike chainring. This will allow me to put the machine's overall precision to the test. Here I have a chainring from my collection, and I don't see any major difficulties for machining, except that the teeth of the chainring have a different thickness than the main plate and are positioned in the middle of the plate's thickness. This means I'll have to flip the piece to continue machining and find a way to place it back exactly in a mirrored position. Regarding the design of the chainring, I want to draw inspiration from my two machines, the Carvera Air and the Key D4 Plus, which I find have very Cybertruck-like vibes. As you may have noticed, most typical chainrings have a very flat style, so I want to try creating some visual depth. I think this inspiration will make for a really striking chainring. After spending a few minutes on Plasticity, which is an amazing software by the way, I settled on this design. I think it really captures the Cybertruck aesthetic, with large chamfers that give a strong sense of volume. Even though the model is already quite precise, I'm going to recreate it in FreeCAD so I can apply variables, allowing me to adjust the size depending on the number of teeth or the type of chain used. This will also make it much easier to generate the G-code for the CNC later on. Once I recreated it in FreeCAD and applied the variables, I was able to get a fully parametric and dynamic file. When I change the number of teeth, everything updates automatically. This allows me to easily switch from a size 44 to a size 50, for example, all without having to change anything in the sketches or operations. That's really the power of CAD software. Let me give you a closer look at the 3D modeling. I started by modeling a cylinder with a diameter corresponding to my chainring diameter variable and a thickness corresponding to the teeth thickness variable. I then created a smaller cylinder in the center with a thickness matching the plate thickness. Next, I created the first opening the size of a chain roller and then used a polar array on this pocket to generate all the teeth. After that, I modeled the different parts to properly mount the chainring on the crankset, such as the central hole and the counterboard mounting holes, spaced according to the BC104 standard. The rest is straightforward, simple openings, a large central one and 4 smaller ones above the mounting holes, with fillets and chamfers to really give it that Cybertruck-inspired look. Before diving headfirst into generating the G-code for the CNC, I made a 3D print on my Chidi 4 Plus. And once again, I'm blown away by its printing speed and the quality of the print. If you're looking for a reliable 3D printer, this is the one you need. I've put a link in the description if you're interested. This 3D print allows me to check my design from both an aesthetic and mechanical perspective to see if everything works. In this case, it's perfect, so we can continue with the project. Before starting the creation of the G-code for the CNC, let me present the attack strategy. As I mentioned earlier, we'll need to machine both sides of the part. On the first side, we'll machine the mounting holes for the crankset and do a surfacing pass for the teeth. Then we'll flip the part over to perform another surfacing pass, as well as machine all the openings and the chamfers. There will be quite a lot more operations on this side. We'll only be using 2 bits to machine the chainring. The one we'll use the most is a 3.175mm end mill for metal, which will handle all the cutting and surfacing. We'll also be using a 3.175mm 90 degrees chamfer bit to take care of the finishing passes, as well as all the chamfers. The chainring will be machined from a 6061 T6 aluminum plate that I found on Amazon for €10 per sheet. Using aluminum will affect the speeds and milling depth, because as indicated in the machine's manual, Makera recommends lower speeds and shallower milling depths. This needs to be taken into account when creating the G-code for the CNC. Speaking of G-code creation, Makera offers its own software for toolpath generation, as well as different profiles for other software like Fusion or Lightburn. If you're a beginner, I really recommend using Makera's software. It's designed to be easy to use and provides a turnkey solution for the Carvera Air. On their website, you'll find plenty of tutorials to help you get started. However, you know me. Despite being a beginner, I chose the complicated way of generating the G-code with my beloved FreeCAD. Unfortunately, Carvera doesn't provide machine or bit profiles for FreeCAD, so I'll have to get my hands dirty and build everything from scratch. I would have loved to share with you the entire modeling process and G-code creation in detail, but that felt a bit too complex and heavy to digest. Let me know in the comments if you'd like a full masterclass on this chainring, where I show you step by step how to model it, how I created the G-code, and of course give you access to the 3D files and the G-code as usual. But let me at least walk you through the main steps I followed. Every CAM project in FreeCAD starts by creating a job. In the job properties, I set the processor to GRBL, as recommended by Makera. I also chose to generate the G-code in the order the operations were created and to export each operation into a separate G-code file. For a beginner like me, it feels safer to split everything rather than running one big file. It helps avoid mistakes. Then in the Setup tab, under the Stock options, I created a box that matches the size of my aluminum plate. I also centered my part inside the stock so that it sits right in the middle. For my bits, I set up a 1/8 end mill and a 90 degrees chamfer bit, assigning them the right speeds and dimensions. I used the new tool manager, which makes it easy to handle and create tools. You can simply pick the bit type and intuitively enter its different dimensions. I'm running FreeCAD 1.1 Dev and I don't think this feature is available in version 1.0. I created 2 jobs, one for each side of the part. On the bottom side, which is the first I'll machine, I started with a 3D pocket where I selected the inner faces of the mounting holes. To make sure the operation works, you need to go into the properties and enable the adaptive pocket finish option, otherwise you'll get an error message. Next, I performed a surfacing operation on the area where the teeth will be. To do this, I created a flat donut slightly larger than the teeth and ran a pocket shape operation on it. This gave me a concentric toolpath instead of one that followed the tooth profile. I found this approach simpler, and it also allowed me to use the same end mill instead of switching to a smaller one. Then I ran a profile operation with the 90-degree chamfer bit to add a small 0.5mm chamfer on the sides of the teeth. I noticed this helps with the chain engagement. That will be only these 3 operations for this side of the part. FreeCAD has a preview tool to check if the generated toolpaths will actually produce the expected shape. And believe me, this tool has been my best friend over the past month. It saved me from a lot of mistakes. As you can see in this preview, everything looks as expected. Let's turn this preview into reality and start machining the part. But before that, a quick message from today's video sponsor, PCBWay. They're a trusted name for both DIY and industrial projects. I had the chance to test their 3D printing and CNC services to create a bike chainring, and the quality was truly professional. You simply upload your 3D file, select your options, and you're set. Their standard 3D printing options are excellent. Plus, every new customer receives a $5 coupon for their first order. A big thank you to PCBWay for supporting this video. The first thing we need to do is properly secure this aluminum plate so it doesn't move during machining. It also has to be placed in the right position. To do that, we'll use this L-shaped aluminum block, which gives me the machine's default origin. This is very important in our case because we'll have to flip the part halfway through the machining, so making sure it's well positioned and firmly fixed is crucial. Next, make sure to press the plate firmly against the block so there's absolutely no gap between them. This ensures that the corner of the plate is perfectly aligned with the machine's origin. To secure the plate, I'm also using these small aluminum blocks along with a few screws to hold it tight against the work area. After that, I remove the L block. You could leave it in place, but during my tests, one of my bits once hit it and snapped. So now I prefer to take it off and add 2 screws to keep the plate firmly fixed. I tried to wiggle the plate a bit to check if it might be loose anywhere, but everything seems solid. The fingerprints also add a nice bonus of grip on the CNC. So yeah, make sure to leave plenty of those. This is the moment to say goodbye to your nice smooth aluminum plate, because it definitely won't look like that once the machining is done. So, farewell and safe travels. I can now open the CNC software, the Carvera controller, and upload my first file, which is the holes fixations. Once the file is uploaded, you can preview the toolpath by clicking the play button. It's a great tool for one last check before machining. We can then run the G-code. In the window that opens, you have the option to check the boxes for a margin scan, as well as auto-leveling, just like on a 3D printer. For the first G-code of your part, I recommend checking all options. When you hit Run, you'll get a message asking you to install the wired probe. That's the part that performs the margin scan, letting you check that there are no obstacles in the machining area. This part also probes different points on the stock to create a height map of the material. It's a really handy option to make sure your workpiece is perfectly flat before machining. Once it finishes auto-leveling, the CNC returns to its home position and emits a sound along with a flashing LED strip indicating the tool number that needs to be installed to start machining. All you have to do is change the tool, then hit the button on top to launch the operation. And that's it. My very first metal machining has just begun. For a first attempt at machining metal, I'd say it went really well. The cuts are clean and sharp, and while there's a bit of material left at the bottom of the holes, it looks like just a thin layer I can easily take off. One problem I noticed is that metal chips tend to stick to the tool, and that can completely ruin the machining. You can see it clearly in this shot. Since I don't have an efficient way to blow the chips away, I went ahead and printed this little turbine I found on MakerWorld. It fits right next to the tool and should help avoid the issue. Next, I moved on to the second step, which was surfacing the area where the teeth will be, removing 1 millimeter of material. With the turbine, you can clearly see the metal chips being pushed out of the machining area, and they don't stick to the tool anymore. The downside is that it throws bits of metal everywhere. Thankfully, I have an enclosure for the CNC to keep the mess inside. At the end of the machining, I could clearly see the tool marks on the metal and thought the surface wasn't smooth at all. But after running my finger over it, I realized the surface was actually perfectly flat. No grooves, just visual marks. I think that's because I used a small diameter end mill, which requires multiple passes and leaves several tool marks. Either way, you'll see at the end that these marks are very easy to remove. I then continued my journey by completing the last step for this side of the chainring, which was creating a 0.5 mm chamfer at the tips of the teeth. I find it easier to do this before cutting the teeth. And once again, the machining went flawlessly. Now we reach the part that could completely ruin the machining. I need to flip the plate to machine the other side. The problem is if I place it incorrectly, the holes could be off-center and nothing would be aligned. So to make sure I don't make a mistake, I put a piece of tape on the bottom left corner of the plate and remove the remaining metal from the bottom hole so that even if I move the plate, I can still figure out how to position it correctly. For this side, there will be parts that get cut out and won't stay attached to the plate. To prevent these pieces from moving and interfering with the machining, I use double-sided tape to stick the plate to the work area. I use my 3D print to see where to place the tape, trying to position it in the right spots to ensure all the loose parts stay in place. I then place the flipped plate, making sure to position it against the L-shaped block, just like I did for the first side. It's really important that the plate is properly aligned against it. I firmly secure the plate by putting all the screws back in and removing the L block. Even though I think the double-sided tape is enough, I prefer to lock everything properly and avoid any unpleasant surprises. Now that the plate is firmly secured again, we can move on to machining this side, but before that, let me show you the G-code in FreeCAD. To start, I duplicated the last two operations from the previous side, which are the surfacing for the teeth and the chamfer at the tip of the teeth. I need these two operations on this side as well. Next, I created a polar array of the path for the small opening. If you know FreeCAD, you're probably wondering how the hell I made this path. Actually, it's pretty simple. I used Tarman's Wire to Profiles and Mill macro. You just create a profile using the base edge, then select the created profile and the edge you want, and it generates a path using the base profile and duplicates it along the edge. It's really nice because it acts almost like a 3D contour, which is an operation FreeCAD doesn't have. Alternatively, we could have used a 3D pocket, but that would have removed the entire opening, greatly increasing the machining time, especially if we wanted to do a finishing pass. So I created this path with an offset of 0.2 mm to leave material for the finishing pass, which is exactly the same operation but without the offset and using the chamfer bit. Concretely, this gives us this result. A first roughing pass with the end mill where you can clearly see the step from the descent. In some cases, this type of finish might be enough, but since we want a professional result, I added a finishing pass which you can see now. The chamfer bit will create the smooth effect we're looking for. Sorry for going over this a bit quickly, and don't hesitate to tell me if you want a more detailed tutorial. Since we have 4 identical small openings, I used a polar array operation to duplicate each of the paths. It's quite possible that the chamfer bit won't cut all the way through the plate, which is why I added a final profile pass to fully cut the central part of the small openings. For the central hole, I used the same technique and Tarman's macro. I did a first roughing operation with a 0.2 offset using the end mill, then the same pass for finishing using the chamfer bit without the offset. However, you can see that around the mounting holes, the toolpath doesn't follow the edge. That's why I created a profile that follows only the edge and duplicated it with a polar array. As with the small openings, I created a profile at the bottom to fully cut out the piece. Then I created a profile along the outer edge before the teeth to make a 1 mm chamfer, giving the piece a bit more character. Finally, I did the contour of the teeth, which will allow me to completely cut the piece out of the plate. I think all of these toolpaths are pretty well optimized to reduce unnecessary movements, but if you have any ideas, feel free to share them in the comments. Let's now focus on the machining. Since I've just flipped the plate, it seems appropriate to perform an auto leveling again, even though I believe the plate is flat. It's the same operation as before. In my case, the holes from the first machining don't interfere with the auto leveling but make sure nothing obstructs the operation. Once that's done, I can put my end mill back in and launch the surfacing operation. There shouldn't be any surprises here since it's exactly the same operation as on the bottom side. By the way, how about we make this machining session into a Build-Lapse with some music? Just wow, I can't believe I managed to make such a beautiful part in such a short time right here in my room. The quality and precision are truly exceptional. Everything is there. The openings, the teeth, the big and small chamfers, everything. It's really amazing. However, I didn't expect the edges to be this sharp when I modeled it. That said, you can clearly see the tool marks. Nothing alarming since you can't feel them by touch. And after a light post-process, they completely disappear, as you can see here. It also gave the piece this half raw, half chrome look that I really like. I think it will look amazing on my bike. In terms of precision, everything is spot on. It fits perfectly on the crankset, and the various nuts work just as expected since I know they are exactly 10 millimeters and fit with almost no play. The accuracy is really impressive. It even feels like this chainring was made specifically for this crankset. You can even see the tiny chamfers I added on the teeth and the outer edge. Honestly, I'm really impressed with the result. Anyway, I really want to thank Makera for supporting me in this project and for providing this CNC. If you're looking for a CNC, whether you are a beginner or a professional, you can go for it with your eyes closed. It's truly a little gem. And I haven't even explored everything yet. It can also handle 4-axis machining and even laser engraving. One thing's for sure, you'll definitely see it again in future projects. If you want to get a Carvera, I have a $100 discount code for the Makera website. It's in the description. I hope you learned something, or at least were entertained. Thanks for watching.